Hello everyone and welcome to Advent of Code in Go. Today we have day 9, I think. So at least we should have, if I remember correctly, we have the ninth. So yeah, let's dive into the puzzle of the day. Okay, what do we have? A rope bridge. This rope bridge creaks as you walk along it. You aren't sure how old it is, or whether it can even support your weight. It seems to support the elves just fine, though. The bridge spans a gorge. Gorge? I don't know. Maybe the pronunciation is a little bit different. Which was carved out by the massive river far below you. You step carefully. As you do, the ropes stretch and twist. You decide to distract yourself by modeling rope physics. Maybe you can even figure out where not to step. Let me. Okay, sorry. Consider a rope with a knot at each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled toward the head. Due to nebulous reasoning involving Planck length, you should be able to model the positions of the knot on a two-dimensional grid. Then, by following a hypothetical series of motion for the head, you can determine how the tail will move. The head and tail must always be touching, diagonally adjacent, and even overlapping. Both count as touching. Okay, I didn't get that. The ropes stretch and twist. You decide to distract yourself by modeling rope physics. Maybe you can even figure out where not to step. Okay, consider a rope with a knot at each end. These knots mark the head and the tail. If the head moves far away from the tail is pulled toward the head. Okay, so far so clear. Due to nebulous reasoning involving Planck lengths, you should be able to model the positions of the knot on a two-dimensional grid. Then, by following a hypothetical series of motion for the head, you can determine how the tail will move. Due to the aforementioned Planck length, the rope must be quite short. In fact, the head and tail must always be touching, diagonally adjacent, and even overlapping. Both count as touching. Okay, these are probably those cases here. So this is head and tail, this is head and tail, and they are always connected. So if you would move this to this position, probably this would move this to that. I don't know. H covers T. Okay, head covers tail. If the head is ever to 2 steps directly up, down, left, or right from the tail must also move 1 step in that direction so that it remains close enough. If the head is ever 2 steps directly up, down, left, or right from the tail must also be. Okay, but now we don't care about diagonals away. So we have tails, head. The head moves to the right. This means tail has to move. Okay. What about here? Head moves to the bottom, tail moves with it. Okay. Otherwise, if the head and tail aren't touching and aren't in the same row or column, the tail always moves 1 step diagonally to keep up. Aren't touching and they aren't in the same row or column. Okay, so this goes up. This means that this needs to catch up so that it goes here. Okay, it goes diagonal because they are in different columns and rows. So and here in this case this goes up, then this also goes diagonal. Okay. You just need to work out where the tail goes as the head follows a series of motion. Assume the head and the tail both start at the same position, overlapping. For example, right for up 4, left 3, down 1. I think that these are a series of motion moves the head to the right 4 steps, then up 4 steps, then left 3 steps, then down 1 step, and so on. After each step, you'll need to update the position of the tail. If the step means the head is no longer adjacent to the tail. Visually, these motions occur as follows. Initial state, then R4 to the right. What does S mean? Ah, S is just the start position, probably. Yeah, okay. Okay, we go 4 to the right, then we go 4 up. This means there are no diagonal. This means up, and then it comes to here. But why don't they... But I would expect that basically the tail moves here as well when this starts to go up. Why doesn't this move then? Let's check again. If they aren't touching, if that is ever directly... If the head and tail aren't touching and aren't in the same row column, the tail always moves 1 step. Aber they are touching. This means if they are touching diagonally... No. So first, basically, we move... If it's 2 up, okay. Alright, from the tail. Tail must also move 1 step. The hook must be quite short. In fact, must always be touching. Okay. Okay, so this makes sense. So then it's diagonally because this is 2 up. Then another, then left 3. So this goes, and this doesn't move. And then it goes another one and it starts to do this diagonally. Okay, then down 1, doesn't move anyway. Right 4. Doesn't move at all because it's still touching. I think it's just moving basically when it's when it's no longer touching. So I think this is the idea. So you only have to move it if they are no longer touching, and therefore you only need to consider where to move the tail when they lost contact, basically. Down 1. Still touching, still touching, still touching, therefore nothing happens. Then it moves over, so they're not touching, therefore it has to go diagonally. Okay. R2, it covers, and then it's... After simulating the rope, you can count up all the positions the tail visited at least once. Okay, simulate your complete hypothetical series of motions. How many positions does the tail of the rope visit at least once? Okay, after simulating the rope, you can count up all the positions the tail visited at least once. In this diagram, S marks the starting position with the tail also visited. And hash marks other positions the tail visited. Okay. 13. Okay, so this is fine. So we have here our moves. Oh, we have here our moves. So, okay, let's get our input and see what does it include. Okay, it's just movements. Oh, and there are large steps in between. Okay, copy over to our new project and store it in this file. Now the problem is we don't know how big the grid is basically in advance. So this is something that we need to keep in mind, that basically the size of our grid, of our input data, can vary. Okay, so let's copy also the example input. Okay. And then let's create our application. Day 09. Yes, want to edit. Oh no, why .do? No, this is wrong. We need to rename. Okay. Okay, so let's think about it. So basically what we have is our type is our grid, or our, how do they call it? It wasn't a grid, it was something else. You should be able to model the position of the node on a two-dimensional grid. Okay, it's a two-dimensional grid. So okay, we keep it with grid. Okay. So, and for that, basically we have our we call them fields, positions, and these are just types position struct. So, and our position can store basically if something was visited or is a starting point or something else. No, we just keep it different. Yeah, maybe we just store it. Starting point is a bool. And then basically if visited tail, bool, and visited head, bool. So it's just basically to know what we already visited. So, and our positions is a slice of slices of positions, or pointers of positions. So a two-dimensional grid. So let's check again with the in the end we just need to know how many positions the tail visited. Okay, so okay. So we don't need to do this for the head as well, but okay. Why not? Shouldn't be problematic. Okay, then let's begin with our input, or starting to reading our input. So input file, comma, error equals os.open test.txt. So if usual, if error not equal nil, and just panic. And defer input file dot close, so that we close it in the end. So we need, the format is again line-wise, so therefore we use our scanner class bef.io.news, yeah, not class, our scanner type. So for scanner.scan line equals scanner dot text. Okay. So what are we reading basically? Our files contains a direction, then a blank, and then the number of steps that we go into this direction. So therefore, I think it's quite easy to parse. So we write some method for that, where we say move is equal parse move from line. Okay, and then let's create this parse move function. So for that we split our strings dot split the line, and we split it on a blank parts if then parts not equal to. So this means we have invalid data, then we just panic format.arrowf invalid move in input file. Okay, so now we have two parts. Then the first part will be the direction. This part's 0. And then we have the number of steps. And this is again some string that we need to convert into a number. So therefore we use our string conf a to I from parts 1. If equal nil, again just panic. So, and now we can return our move. So let's create a move class or type move, which is a struct, and the move has a direction. How do we create enum types? Is this direction? I wouldn't not like to use type direction enum. Is there something like that? Okay, let's check out enum. I think there was some way. Didn't we use this somewhere? Ah, yeah, this was it. Okay, we just create consts for that. And then string methods to enum type. This is basically what we need. Ah, okay, then we just need this. Okay. Okay, then I remember this page, so we looked at this before. So we have our const that we call direction. This is up, down, left, or right. And type direction from this type string. Okay, now can we cast this to direction? Yeah, it seems we can. This is nice. Okay, good. So now we can create our move that has a direction and has a number of steps. And then we return our move. Move from direction, steps. Okay, so far for the parsing. So we can now just print it. Just see if we basically parse everything right by just printing our moves. Move. For that, maybe we just create a toString method for this type as well. Func and move string return format.sprintf. Times %d. So, and then we just say this is then m.direction and m.steps. So now let's try to run this and see if we basically get the same output that, or basically the output that is corresponding to what we are reading. So it's trying to build it. Let's see, set our test there. So first is r times 4. Okay, this looks good. Okay, so parsing seems to work, which is nice. Now, what do we do with this? So basically, now we have the move. So we can just implement a new function within the grid that basically would updates the grid based on how we are moving. So therefore, we create our grid. And we just create a new one. Grid. And then this grid gets a new method, func g. Okay, and we always use a pointer because otherwise we don't want this grid to be copied. And we just tell it move, and it gets a move object and doesn't return anything, so it doesn't update it, it doesn't return it. Okay, so what we are now doing. So first the grid needs to know where we are. So this means we need to store our position, and this is something that we can do by some set of coordinates. So within our positions, or maybe not grid positions, position is probably not the correct term here. Let's use something else. Let's use field. Fields. Okay. So within this grid, basically we start at the position 0, 0. Yeah, which means the bottom left position at the beginning. So this means when we now have a move function or a move, we get a move, then it depends basically on where we are. And what we need to do. So first, if we are at position, for example, we are moving left. So it depends on the direction. If move dot direction equals, for example, if we are left, if we want to go left, and we are already at the topmost leftmost position, so if x at g dot x equals 0, then we need to expand our grid, right? So this means basically what we are doing, we are go through all those fields and replace the fields in there. So because we need to shift everything which is in there to the right. So for that we do this, we loop over the rows in g.fields range, again range. So, and each row we replace basically with a row that contains the same content, but has one element before in addition. So we say our new row is a new slice of type field, or pointer to field, with the size being the length of row plus 1. Yeah. So, and then we copy over between those slices. So we copy everything from the old row into the new row for e so e smaller len dot row len from row e plus plus, and then we set new row e plus 1 equals row from I. So, and for the new field, basically we just create for the first field we just create a new field. Okay. And then when we are done with that, we need to when we are done with that for this row, we need to update also our x value. So we need to say g.x g.x is 1. So we basically move it one time to the left, to the right, so that it's not not standing at the last position. Okay. Good. Why is this wrong? Evaluated but not used. Ah, yeah, we need to replace the row, of course. So we need to say row index g.fields from row index, and this is equal to new row. Okay, so this is what we do when we have to go to the left. So now we need to do these things in the same way basically for the other direction. So else, if move direction is bottom and we are already at the lowest down, was it not bottom, down, and we are already at the lowest position, then we do basically the same thing, but we don't have to replace the row, but we just or replace the rows and make them one longer. We just add a new row at the so therefore we create a new row which has the length of just the first row. We can just use the first row. And then we just append this. Oh no, we don't append it. We copy over the old rows. So we say g.fields old rows is equal g.fields and new rows is equal make. Here we now create a new slice which contains the rows, so basically a slice of slices of field, and the length will be basically the len of old rows plus 1 because we are adding a new row. So and then new rows from E is old rows. So we do basically the same, just shift them to one position up. And then we say new rows 0 is then new row. That's something that we can do here. And then basically we replace our G fields with our new rows. And in the end, we move our y coordinate to be 1. Okay, so for left and down, we now have those things. And now we do the same for, let's start with right. Because now we need to push from to the other direction. So if we are right and g dot x is equal, not 0, but now if it's equal to the len of g dot fields. So if it's basically equals to the length of the individual rows that we have. Yes. So if this is the case, then we again create a new row. For all rows we need, all rows need to be extended. So we create new ones, but then we basically copy the new row and then add len from g dot fields 0, because this is now the last position. This was the last position before. And now we made the rows one field larger, so therefore this is now the new position. We create there a new field, and then basically we exchange the row. And we set g.x. No, we don't need to set it, because now the field got larger, and therefore the position is fine. Okay, so this was easy. And let's now do this in the same way for move up. Direction is up, and our y coordinates is len from g dot fields -1. Then we do basically the same. We have our old rows. These are kept. And we create a new set of rows, which is one row larger. We copy over those rows. We create a new additional row. And then basically we just set this to length of g dot fields -1. Is this correct? No. So, and then we add y coordinate stays and we set our new rows. Okay, so this should now give us basically expanding grid, right? So with every move, basically, we can now expand. So this means that after this handling here, basically we can just go into the direction where we need to go. So if left, direct move dot direction equals left. Then what we do is basically just move directions equals left. Yeah, then the only thing that we need to do is change the x coordinate, right? Because moving to the left means we decrease it. So, and now the problem is now that we have multiple steps. So our move has the number of steps that we need to go. So, and the easiest way to solve this would be to go always into the direction, to basically call ourselves recursively. So what we can do something like this. So remaining steps, we can do this for all cases. Remaining steps equals step move dot steps minus 1. And if remaining steps greater 0, then basically we call us recursively. And we do something like this, where we say g.move, and we create a new move that has the same direction. Move.direction, but has only remaining steps. So, okay, now let's do the same handling here for other cases. Else, if we can just copy and paste this. Okay, left to the right, and in right we add 1. Then we have top to, no, not top, down, where this is y, and we remove 1, and we have up, where we add 1. Okay. So this should now create our should now make sure that our grid is always kept and always grows into the direction that we want. So now it would be a good time to test this. So in order to test this, it's nice to have something that we can see, right? To visually inspect this. So therefore we create a new function that we use on our grid. Draw grid. And this is basically just looping over the individual rows, but from the other side. So we need to reverse it. For y, len from g.fields -1, y greater equal 0, minus y minus minus. And now we just print it. Print for x equals 0 to x smaller than len from g.fields y x plus plus. So and now we check basically what we should print. So if x equals g dot x, so if this is our current position, and the same holds true for y, for the y coordinate, then basically we just would print there some format for print. We just print there, what do we use? A star. We are the star. So therefore else In another case, we just print for this one, for an empty field, we just print a dot. And then when the row is finally printed, we can just call print line. And this is what we do for all those fields. And in the end, we should draw the grid. So in order to have a separator to the grids we saw before, we just have here a small separator. So, and now we pass those individual moves, print the move, and then basically we apply those moves, move, move, and then we also print the grid, draw grid. So, and this should allow us to inspect basically what we have done, if this makes sense or not. Okay, let's debug. I think makes sense here. And see what happens. Okay, we have our first move, and probably it doesn't work because our grid is empty, but we'll see. Okay, there's some error. This fatal panic, yes, of course. Index out of range 0, yeah, of course, we didn't initialize our grid correctly. Because currently the grid is empty, which means it doesn't have any fields, which is obviously wrong. Because it should have a slice of a field. Is this correct? Can we do this? Missing expression. Somehow it doesn't work. The composite literal allocates a new slice instance with the given values. Yeah, it should. So we want to create this. Missing expression. Okay. First row, then we do it manually as make. Or can't we do this that way? Okay, maybe this is what we need to do there. So this is, and this is then a slice of slices of field. Ah, now this looks better. So we initialize it with an empty field. It doesn't look better at all. Okay, no, it looks somewhat better. So we already moved a couple of times. So we began with r equal to the 4. So this one, maybe we should draw the grid before we actually start to move. So we only have one position. Okay, makes sense. Then we pass the move, and we move, and we draw the grid. Remove the breakpoint. Okay, so we go 4 times to the right, we go 4 times up, but this doesn't look correctly, right? If this is 4 times up, this would mean that we would have afterwards 4 Yeah, 4 lines or 4 rows, but we only have 2. So I think this is somehow broken or not correct. So let's check. In this case, we have our up case. Ah, yes, we need to move in Y direction, obviously. Okay, stop and rerun. Okay, now it looks a little bit better. So we start here, then we go 4 times to the right, then we go 4 times up, which is here. Then we go 3 times to the left, then we go 1 down, then we go 4 times to the right, and then it somehow breaks. Okay, so there's probably something wrong in our initialization for the right. If move direction is right and x is equal to the length of the fields minus 1, then okay, let's see what happens here. Okay, I think this will be the case where we need to look into. So now it's the case. So we have R4 and we are at the so x is 0. Why is this 0? Ah, this is the initial. Okay. Oh no, just continue. Okay, so let's see how our new row looks like. So its capacity number has 6. So our position is 0. No, our position is gx is 4. And this is then 5, correct? Yeah, this is 5. And in 5, we just create a new field. And if we do this for all rows that we have, oh, runtime index out of range. I'm a little bit puzzled because it worked the first time. So therefore I'm wondering what is so different when we call it the second time. So jump over, jump over, jump over, jump over. Okay, now this is the case. Jump, 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 jump. Remaining steps was 1. So g.fields. Okay, they have all the lengths 5. Oh, there are nils. Nils doesn't sound correct. There are a lot of nils. Why are there nils? Okay. I think there is something wrong. Because if we create new rows, we also need to initialize them. Okay. This means for everything like up and down, we need to make sure that our new row is properly initialized. So for E then we need to create new fields that they are pointing to. New row E equals address of field. And this is something that we also have to do when we go down. Yeah. Okay. It's probably not the only arrow, but it's one arrow. Okay. Next, 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 next. I'm wondering a little bit about this call stack. Remaining step is 2, remaining step is 1. But we will see. Okay, now let's look at the individual fields. This is complete, this is complete, this is complete, this is complete. Okay, this looks better now. But we are still having this issue that we are now going to crash. Okay, we create a new row. Sure. This is now 6 long. Len from row, this goes to 5. Yeah, because we copy all 5 instances. Okay, this is correct. So we copy, copy, copy 1 till 5. Okay, and then okay. And G fields row index is equal new row. Okay, so far so good. So row 1 worked. And row 2, bam. Okay. Stop and rerun. Here. Okay. 1, 2, 3, 4. Okay, and now we need to do this for the individual. This is the first, and this was the second. So, and why is this now length of 6? Ah, okay. Because we already increased the size of the first row, and therefore why do we need to use the current row, of course, not the first row. And this is probably the same issue here then later on. For old rows. No, this is fine. Okay, do we have the same thing with when we go to the left? No, we use already the row index. Okay, so this is fine. Okay, let's see. Let's run now. Okay, this looks better. So we were here. We go 4 to the right, then we end up there. Then we go down 1, which is there. Then we go 5 to the left, which is there. Then we go 2 to the right, and then it's there. Okay. Nice. So this seems to work so far. Now let's print also the way. I think it might be useful to have this as well. So to draw a grid. Else if g dot fields y x dot visited head. So we say everything that was visited by our head. Then we just print. What do we use? Just use an O, a small O. Else. Okay, let's print again. And now we should. We don't set visited head. Okay, this is g dot fields. G dot fields. G dot x. Y. G dot x. For visited head equals true. Okay, now these are all the fields that we run again. This way, this way, this way, and then back. Okay. Good. So this, let's compare it to what we basically should come up with. Yeah, I think the head position is correct. So if we just try to, yeah, okay. Okay, now let's think about the rope. After simulating the rope, you can count up all the positions the tail visited at least once. Okay. Assume the head and the tail both start at the same position overlapping. Okay, good. So this means basically we just need to keep track of two different positions, right? So we have our x, head x, and our head y. So this is basically what we need to replace in all those places. And just the head x, head x, head x, head x, head x, head y. Okay, head y, head y, head y, y, head y. Okay. There's still something missing here. Ah, there, head y. Okay, and if we know the position of the head, we can also know the position of the tail. Tail x, int, and tail y, int. Okay, and now we just need to think about the position of the tail. So this is basically the move of the head, and now we can create another method which takes the head position and basically updates the tail. So therefore g dot move tail, and move tail is something that will happen automatically, so it doesn't need any input because it's only dependent on the state of the grid. Move tail. So therefore, we don't need any return type as well. So now, how were the rules? So if they are touching, we don't need it. So how can we define if they are touching? So this means basically they are only not touching when the position, or the difference between the position of them is greater than 1. So it's 2 in any direction, right? So this means, so if x, g dot tail x minus g dot head x, and then we need the the absolute of this. Yeah, is there some math library for that? Golang apps. Where is it coming from? Math. Okay, yeah, math could have been. Ah, it's automatically to. Do we have an ups int? Int. Compute absolute value of an int float. Upsdiff int. Yeah, okay, this is something that we can implement. So upsdiff int. Yeah, this is nice. This is the condition that we actually need. Okay, going back. So if g dot tail x smaller than g dot head x, then g dot head x minus g dot tail x, else diff x is an int. Then diff x, which contains just the difference between both positions, as diff x equals g dot tail x minus g dot head x. So, and the same thing we basically do for the y direction, the y coordinate. Head y, 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 head y. So, and now we need to check. We only need to move if either diff x or diff y are larger than 1. So, if diff x larger 1, else if diff y is larger than 1. Maybe we do it differently. Maybe we need to I think it doesn't make sense to call calculate the difference here, because we need the direction. We need to know in which direction we need to move, so therefore it's probably okay if we just do something like that and then have in the end different conditions based on the sign of def x or def y. So if def x is greater than 1, else if def x is smaller than -1. This is the other case, right? So def x greater than 1 means that the head is more to the right than the tail. This means the tail has to move to the right. If def x is smaller than -1, this means that the tail is larger than the head. So this means the tail is more to the right, and if we go into the left direction, then basically we need to move the tail to the left. So, and then we need to check basically if there is if also the y coordinate is different or not. So if y equals 0, when it's equal 0, this means basically they are on the same row, so this means we either go to the left or to the right, so we can just move the tail by 1 into the correct direction. G.tail x is equal to, we just go 1 to the left, no, to the right, plus equal 1. Okay. For the other case, we need to go 1 to the left. Okay, but this were the easy cases. So now, if diff x, diff y equals 1. So this means basically that the head is 1 line above the tail. So this means we need to be to go diagonal. We need to go one up as well. So this means, okay, this is something that we can do anyhow. So if it's, then we need to say g.tail y. It also goes +1. So we also need to go in the direction of the tail. Else, it could also be -1. It could also be -1, which means g.tail y needs to go down. So, and we move to x and all. in either cases. So, and this is basically the same what we do now here, but we just do it in a different direction. So we do it the same way, but just in the different direction. Okay, so far for going into X direction. Else. Now let's do those things for Y. So if diff Y is equal we just change it or replace them. So let's check if this makes sense. So if diff, let's close those. So in case diff Y is larger than 1, this means that X is 2 times higher, so is higher than Y. Then head is higher than tails. This means basically that if X is also higher, we need to go to the right as well. And if it's not, else if diff X equal -1. I think this is some condition that we also add here as well. That is missing here. Yes, this is something that we should do. We only need to update this if this is also goes into -1 direction. We only need, yeah. Okay, so this means that by the end, we have moved the tail into the correct position, and then we just set this to visited head, visited tail. Tail Y, tail X. Okay, so and how do we print the tail? Tail X, tail Y. Then tail is our, I don't know, our box, our D. Just use T. Our tail is currently D, and if something has been visited, the tail has been visited, I think this is more important than the other way, because tail is actually what we need to calculate in the end. We print this hash. Okay, let's run it and see what happens. Okay, our tail goes to there, goes to there, goes to there. This is tail, this is tail. I think there's something wrong, but we will see. Okay, we start here. So this is basically our tail. Then we go 4 times to the right. So this is here. Then is this correct? Let's compare with the solution. Go to the right, then it goes up. Yeah, and then it jumps. Okay. Ah, yeah, okay, and this was only visited by head. These are visited by tail. Okay, this makes sense. Then we go 3 times to the left, so this is also not visited by head, but by tail, by tail, but only by head. Then here, then we go down 1 thing, then we go 4 times to the right. So there we don't jump, there we don't. Yeah, we jump then. Yeah, okay. Okay, let's compare that. We go 3 to the right. Then we are here, then we go there, then we go right, then we go there. It jumps diagonal. Then we go there, then we go there. Then we go back to the other side. Then it jumps. Okay. We are here, then we go to the left. Okay, yeah, sounds okay. So now let's think about what is the number that we need to. There are 13 positions the tail visited at least once. Okay, then let's think about. We need to calculate this, but this is quite easy because in the end we can just count all the positions where this tail visited, or how did we call that? For x, no, y. Zero. For no, we need the numbers. For y equals 0, y smaller than from g dot fields, grid fields minus, no, this is fine, plus 9, y plus plus. The same now for x coordinate, then field y x tail count tail if grid dot fields y x dot visited tail, then count tail plus plus, and then in the end just some print message tail visited fields. So, and I think it should be 13. Okay, tail visited 13 fields. So far, so good. Now let's, at least this is the same 13 that we have here. So therefore we can be quite sure that this is not completely wrong. So let's try to do this on our real input data. Input.txt, run it. Okay, it becomes way larger. Okay, maybe printing it out every time is a little bit too much, but one could imagine it as art. Okay, so printing it out is definitely not the best idea How many input does this have? How many lines? 2000. If we now knew which move we are at. Okay, we just do this now without graphics. Oh man. Okay, process finished. 5,890 fields. Okay, so printing it out is way more problematic than just calculating it. So let's see. No, that is not, your answer is too high. If you're stuck, make sure you're about full input data. Our input is too high. Okay. Let's go back to the browser and see if we missed something. This use of motion move the head right 4 steps, then up 4 steps, then left. After each step, you'll need to update the position of the tail, as the step means the head is no longer adjacent to the tail. Visually, these motions occur as follows. Nee. The tail aren't touching and aren't in the same row column. The tail moves 1 step diagonally to keep it up. These are all the cases that we have and must always be touching. Okay, then maybe debug through and see if we see something awkward or wrong. And hope we can find some answer there. Two times to the left. Okay, this is already wrong. This should be already, since this is the starting position, this should be already marked as something that the tail visited. Okay, then maybe we set this for our new field that we create. We set visited tail and to true and visited head to true. Okay, but now this will only give us more. No. Don't draw. So this is basically what we added here, where we say this visited, but it's still 5,890. Okay, good, then go step by step or continue step by step. So 2 times to the left. This is not correct because this is basically okay, we need to debug through it because currently the tail should be here in this position. Okay, easy. Okay, we need to do this in move. Oh no, maybe in pass the move should be fine, but the tail is not correct. So let's go there. So now, after the first move, head and tail are basically at the same location in Y X-ray. No, this doesn't make sense. Okay, we need to start over from the beginning. This doesn't look right. So we start with our first move, and our first move is just going to the left. So this means our x is 0 and we go to the left. So this means we need to okay, the problem is that we need to change the position of the tail as well. If we add a new column before or a new yeah, okay, this makes sense. Okay, this also means that g.tailx plus plus. So if we add a new column, then we need to update the position of the tail as well. So, and in the same way, if we add a new row, we need to make sure that our tail y coordinates is updated accurately. So from the right and up, we don't have those problems because there we don't move the coordinate system, but the coordinates can stay. Okay, let's see again. Now it's -1. So this is not updated. Okay. Then in the next, it's -2. So we need to update it. So we go in there and we just move it to the left. Okay. So let's see what comes out if we don't draw the grid. So 5,890 was the old solution. This is 5,883. Okay, at least somewhat smaller. If it's small enough, let's see. Yes, okay. Okay. Hi, this took longer than expected. A rope snaps. Suddenly the river is getting a lot closer than you remember. The bridge is still there, but some of the ropes that broke are now whipping toward you as they fall through the air. The ropes are moving too quickly to grab. You only have a few seconds to choose how to arc your body to avoid being hit. Fortunately, your simulation can be extended to support longer ropes. Rather than 2 knots, you must now simulate a rope consisting of 10 knots. 1 knot is still the head of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in front of it using the same rules as before. Okay. Okay, so this means basically we now have 10 knots. Okay, instead of just those twos. So this means we need to modify our solution quite a bit, because currently this 2 is hard-coded, which is not nice. But we can manage. Okay. Now you need to keep track of the position of the new tails, and we also get a new example. Okay, then let's copy the example and start working on it. So, test2.txt. Okay, so how can we do this? So the easiest way would be just to... oh no, what in the end do we need to print out? This is the example, what needs to come out. Simulate your complete series of motion on a larger rope with 10 knots. How many positions does the tail of the rope visit? At least once. Okay, tail are everything besides the head. Okay. Okay. I see. This means we probably need some new data structures. So where we in the beginning had the tail here, we need to have multiple tails. So therefore we add some new type. There we say knot. And a knot has basically the X position and the Y position. So, and then we have our head, which is a knot. And we have our tail, which is basically a slice of knots. Let's do it this way because we need to update them. We need to update those positions. So this is so far so easy. As a start, we just update everything in here so that basically this should work. Tail and that this works also with our new our current solution works basically correctly with the changes to its implementation. So, and this is same here, dot x, dot x, dot x, dot x, dot x, dot x. Oh man, there's so much going on. Yeah, this is definitely something that will change. Because this becomes then a function of our knot class. So, and now the tail needs to we first start only with the first of the tail. Okay, head dot x, head dot y, head dot tail. Okay, so let's see if we now run it, if we still get the same result. Oh no, yeah, of course we didn't create the grid correctly, because now we don't only need to specify the fields, but there's also now the head, which is a new notch, and tails, or tail, which is also a knot, but now a slice of knot. Okay. And 5,883 fields. So this is nice. So we use this basically as some regression test now to see if this actually destroys anything. So, and now what we would need to change. Oh, okay. So basically what we did here now is just go through all those things and extract this new class knot. And instead of having here head X and having head tail, we can directly represent this as knots, and then we just need to access those components in between. So what we now need to do is that basically that the tail is now consisting of multiple things. So, and each tail basically depends on another tail. So therefore we can basically make sure that, no, we can always tell the tail what is its previous node. So that we say previous knot, and this is then a knot. And then basically, no, this. And then we replace the head with it. So we say previous knot X. And this is then no longer a class of the tail, but it's of the knot. And here, therefore, we would only have here K. Not Y, not Y. So this makes it a little bit easier. So the only problem is that in the end we need to access the field, but this is something that we can move out. This is something that we can move out to the place where we actually call move tail, and this is here. So, and this is then basically where we say move tail, and we give it the head as the previous. And we don't call it on this, but on the tail. dot move tail. So on the first of the tail, basically we just call it, so it should move depending on the head that we gave it. So this should be functional equivalent to what we did before. And we see, okay, we are still at 5,883 fields, so this sounds quite good. So, and now if we have multiple tails, so this is basically the problem that we currently have. At the moment we only have 9 tails, but we need to do this for all tails. So therefore, for previous tail is g.head. So, and then for tail in range g.tail, and for all those tails, basically we move them one after another, where we say tail dot move tail depending on this one, and we update everything that is basically where the tail is currently will be set to visited tail. And we say previous tail is equal to tail. And this is then basically previous tail. Okay, so this should now be compatible with multiple tails, but we still have only one, so we get the same results yet. So draw grid. Okay, then let's see if we can adapt draw grid as well. So we need to draw the individual tails. So how were they drawn in the example? Head and then 1, 2, 9. Okay. Okay. This means we need to loop. So if it's then else. How do we loop over it? Okay, we just do something like that. Continue. And then we do a loop for tail index, tail in range g.tail, and then basically we loop over the individual objects of the tail, and then we check for their position and then print out the equivalent number. Coming from e to r, from tail index +1. Tail. And then also continue. So continue just to make sure that we don't need to go into all these cases that come up later. So, and then if we didn't continue at all, then we basically check if something was visited or not by the tail or either by the head. Okay, so far so good. Let's run it. And still works. Okay, now let's print out some example for test2. So we have test2.txt. Just draw the grid. That should be shorter. Okay, this was only a grid now with where we had the tail that contains only one single knot, but as we said, we need more. We need more. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we need 9 knots in the tail. You run it. Okay, and let's start from the beginning. Okay, we first go 5 to the right. This doesn't look correct. I think our way how we print stuff is off. fx 5, 6, 7, 8, 9. Because this doesn't seem right. But I don't see the problem here. So we loop over. Oh no, not continue. We need to continue in this. Oh man. Okay. Found tail equals true or false. Then found tail is equals true, and we break the inner loop, and then if we found a tail, then we continue the outer loop. Okay, this is not really nice, but I think it should work. Okay, let's start to beginning, go to the beginning. Okay, this looks way better. So we go 5 to the right, so we have here our, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. This doesn't look correct. Is it correct? Initial state. R4. What did we do? R5. Okay, we are comparing the wrong example. Okay, then let's compare it again. Or is there some... here, this looks better. Yeah, this is how we had it also, and then 1, 2, 3, 4, 5. Okay, but this looks different. Hello. So this looks, so the first 5 steps look similar if we compare to here, but then after we go 8 times up, this is not correct. So 1, 2, 3, 4. 1, 2, 3, 4, 5. This is fine. But somehow this is different. So 6, 7, 8, 9 should be just a diagonal. And for us, it's 6, 7, 9, 8. Okay, did we implement some error when we moved this move tail? So we always keep our previous tail. This is really worrying. Okay, let's look again into the... Maybe we implemented something wrong. Now you need to keep track of the position of the new tail. 9 visits. In this example, the tail never moves, so it only visits one position. However, be careful. More types of motions are possible than before, so you might want to visually compare your simulated rope to the one above. Why are more visible? Okay, then let's test it with the initial one. You must simulate a rope consisting of 10 knots. One knot is still the head of the rope, moves according to the series of motions. Each knot further down follows the knot in front of it using the same rules as before. Using the same series of motions as the above example, but with the knots marked H1 to 9 to the motion. Okay, let's compare it one by one on the original test input. Test. And then also print it out, the grid after each step. Okay. So now, okay, we went 4 times. Right, next. Okay, this is definitely wrong. 1, 2, 3, 4, and then 5 and 6 are below. This is definitely not going to fly. Okay, but this is nice because this is something that we can easily check and see why it doesn't move. Why the 5 is still there. Okay, so try again. Start debugging. We jump over the first move because the first move was correct. So now go into it. Step into. So we assume that the head movement is still working because it's basically the same as we had before. So therefore the only part that we need to consider is basically the tail. So our previous tail is, okay, it's a pointer. So tail.move tail. So now we just compare. The difference is 1, 1 in every direction, so therefore nothing happens. Okay, sounds good. Going to the next. So now the next tail. Difference is 1, 0, so also nothing happens. Oh. let's do this. So 1 0, so nothing happens. 0 0 0 0 0 0 0 0 0 0. Okay, now we are in more interesting parts. So our previous knot. Who was the previous knot? 4 2. This is probably the head. Let's see. Okay. So this means we have now y is greater than 2, so therefore our x direction gets increased, no, gets not increased, just our y. But why? No, 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 no. If diff x is 1, then kx was increased by 1 as well. If difference in x. So now we are in the same. Okay, and now we go up 1. Okay, this makes sense because it was a diagonal move. Okay, next one. Now the next one has the position 4 1. This is the one that we calculated. And now the problem is that no, it's not a problem. Def x is equal greater than 2, so difference in y direction is 1. Therefore we also move in y direction, which is what we do here. And we are now at 3 1. Okay, sounds good. How do the trees, the tails look like at the moment? 4 1, 3 1, and then 1 0. This will be then 2 1, and this will be then probably 1 1. And this will 2 1 1 1, and then this will stay 0 0 0 0 0. Now it's 2 1. Now for the other one, the difference is also 2 1. Therefore we go one direction in y direction and one in x, so that it's 1 1. And now the difference for the next will be all 1, and therefore we don't update their position because they are adjacent to each other. Okay, okay, so next. Now we updated head. Head is 4 3. Now our tail is 4 1. So far correct. So our new tail is 4 2. Then three 1. 4 2 3 1. No, this doesn't look right. It should also. It shouldn't move at all. So they all stay the same. Okay. Next, 4 4. 4, 3. And now 3, 1 should go to 4, 2. 4, 2, okay. And now 2, 1 should go to 3, 2. Correct. And now 1, 1 should go to 2, 2. Okay, also correct. And then the 4 should go to 1, 1. Ah, no, the problem is now. Ah, I see. The problem is now that we have also movement in diagonal. Before we could the head could only move either up, in vertical or in horizontal direction. Now the previous node can also go in diagonal direction, and this is basically the problem because we don't handle this well. The question is, how is this defined? So currently we think, okay, if we go into X direction, then we let's think about what is the expected outcome here. Okay, this is greater equal. And this is smaller equal. Greater equal because we should also go into this direction if the distance is 2 and not only if it's 1. And I think this is the case. Therefore, we probably don't go into the correct direction. We don't correct into the correct. So let's go over it, right? Just say, okay, here we now calculate this is probably 1, 0. Yeah, so we don't correct for the y direction. And this is wrong. Okay, now with the changes, let's see what now happens. Syntax S. Ah, okay. Okay, I'm not sure if this is correct. 1, 2, 3, 4, 5, 6. Let's compare. 1, 2, 3, 4, 5, 6. Okay, this looks good. Then it's L3, which is in the end H 1, 2, 3, 4, 5, 6. Let's compare that. H 1, 2, 3, 4, 5, 6. Okay, this looks also correct. D1. H 1, 2, 3, 4, 5, 6. So this is just this. Yeah, okay. Then R4. In the end, 1, 2, 3, 4, 5, 6. Okay. R4. 1, 2, 3, 4, 5, 6. I'm sure. No, this looks different. Oh, does it? No, 1, 2, 3. 1, 2, 3. No, it looks the same. Okay, this is actually quite good. Let's check the last one, which is Once, 1, 2, oh man. 1, 2. So the 2 is covered. Yes, this is actually quite well. Okay, so for our first input test, this seems to work. Let's compare the other one. So we start our test 2, run it. And tail visited 234 fields. And then in the end we have this. Okay. Browser, larger example, and in the end the example looks like that. Okay. Now the tail visits 36 positions, including S at least once. How many did we calculate? Tail visited 234 fields. Okay, there seems to be some misgap. So, tail visits 36. Ah, okay. So the problem is, I think I understood the problem. The tail is no longer, or not every part of the tail basically marks that it's a tail. So at least here, this looks more or less that only the last one. Here, this is also now the tail, and in embraces 9 visits 36 positions, at least one. This means we need to change how we mark our tail as visited. This is something that we just do then only one time, and after this, so where we say g.tail len last tail is len.g.tail -1. So last tail y and g.tail is visited. Okay, let's run again and see what happens now. 40 fields. But it looks somewhat better. But why 40? Compare. $36, and why is this 4 more in our case? Okay, this is 4 times there, and then the starting position. Okay, doesn't help. The only solution is to go through the initial state and then see what changes in between after the individual moves. Okay, so let's do that and see where we are different. Maybe just adapt shortly the print method so that we have the head there. as H. Okay. And run after draw grid. Console. Okay. This is our starting position, which matches our position here. So H1, 2, 3, 4, 5. H1, 2, 3, 4, 5. Okay, next step. H1, 2, 3, 4, 5, 6, 7, 8, 9. And 9 is still at the starting position. And here it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And S is still in the starting position. So far, so good. Okay, now let's compare L8. Next step. Okay, and here, okay, this here doesn't look right. Ah, okay, I know what we did. Basically, the problem is we only update the positions of the first tail. We don't update the position of all tails when we extend the grid. This is something that we totally forgot. So here, basically, we need to do those updates for the whole tail. This is obvious. Oh man, so much problems today. Tail. So we increase the tail by 1 and the x coordinate, and here the y coordinate by 1. Okay, now let's run again. And now it's 36 fields and it looks way more than it did before. I'm still a little bit puzzled about this disconnect here, because this would mean that basically, no, this can't be true. That this is basically jumping. So why? Why is it jumping? Let's run again. Okay, it was just a rendering artifact. Okay, so this now looks good. Okay, I think we can be confident and try to submit our solution for the input that we got. So just go to input.txt and run it. We should remove the grid, run it, and we had 2,367 fields, and then see, submit. Oh, okay, finished. Ooh. Okay. So this was definitely a little bit more challenging and a lot of room for potential problems. We saw that basically changing and adapting code always needs to be done in all places. So this is, I think, a lot of the time that we spent and searching for bugs was basically due to us only making changes in half a way. So this is something that we can improve on. But we will see. In the end, we got the solution, so therefore, good enough. Let's see how long this will continue, this streak. So, have a nice evening, everyone, and see you tomorrow.